Okay, so we're going to talk about sequences today. All right, so suppose you have a round, flat cake. Okay, and this is a mathematical cake. It's completely flat. It's not a real cake, so you can't slice it. It has no thickness. Okay. So with one straight cut, you could cut the cake into two pieces, right? So I just make one straight cut anywhere through the cake. I got two pieces of cake. Not necessarily equally sized, but I have two pieces. Okay. What's the maximum number of pieces you can get with two straight cuts? 4. So I have it drawn there. So with 0 cuts, you get one piece, right? One cut, you can get two pieces. With 2 cuts, like this picture, you could get 4 pieces. With 3 straight cuts, like I have drawn there, how many pieces? I got 7 pieces. 1, 2, 3, 4, 5, 6, 7. So by being strategic, I can get 7 pieces. Okay. How about with 4 straight cuts, like I did in that other piece? In this last piece, I have 4 straight cuts. 1, 2, 3. So I have 1, 2, 3, 4, 6, 7, 8, 9, 10, 11. 11 pieces of cake. Okay. So I have a sequence of numbers, right? The number of pieces I can get when I increase the number of cuts by 1, right? From 0 to 1, or 1 to 2, or 2 to 3, or 3 to 4. My sequence of numbers of pieces that I can get is 1, 2, 4, 7, 11. And so maybe there's some kind of pattern here. Maybe there's some kind of pattern, and I could guess how many I would get with the 5th cut, because these pictures are starting to get messy, right? And it's hard to count. You think 16? That's a good conjecture. We'll put that guess here. Come back to it later. Okay. So we'll come back to this problem later. Okay. So a sequence is just a list of numbers. It can be finite, like 2, 7, 20. That's a list of numbers. Or it can be infinite, like 2, 4, 6, 8, 10, 12, 14, 16, etc., etc., etc. The numbers can be random, like in the first example, no pattern at all, 2, 7, 20, right? Or they can have a pattern, like in the second example where each number is an even, right? That's the list of all even numbers. Okay, so some notation that we use around sequences, around lists of numbers. Okay, we usually name a sequence with a letter. So for example, we could name the sequence 2, 4, 6, 8, 10, 12, etc., etc. We could name that sequence A. Okay, so we now have A equals that list of numbers. And we name the terms of the sequence. Each specific number in the sequence is called a term of the sequence, and we name them using a subscript. So the subscript is like a little number in the lower right, looks like an exponent but down instead. Okay, the subscript tells us where in the sequence to look. So it's like the address of the number. Okay, so if I ask you what A3 is, A sub 3, you would answer 6 because 6 is the third number in the sequence. Okay, so A sub 3, 3 is like the address, and 6 is the number that lives there. Okay, so what would A5 be? 10. Good. The 5th number in the list would be 10. Okay, so we're going to try to establish a mathematical way of describing the pattern. In English, we could say, oh, 2, 4, 6, 8, that's the list of even numbers, right? But I want to describe this list, this sequence of numbers, using this new notation with the subscript. So A2, what number is that? 4, right? The second number in the list, is equal to A1, which is what? 2, plus what? Right, plus A1, which is 2. Good. So A2 is equal to A1 plus 2. A3, which is 6, is equal to A2, which is 4, plus what? A1, which is 2. So A3 equals A2 plus 2. A4 equals A3 plus what number? 2. And A5 is equal to A4 plus what number? 2. So any number in the list is equal to the number before it plus 2. Does that make sense? So that's what these subscripts are telling me. This says that A2 is equal to A1, right? Plus 2. And A1 is the number right before A2. And if A3 is equal to A2 plus 2, A3 is the third number in the list, and A2 is the second number in the list. So this says that A3 is equal to the number right before it plus 2. And A4 is equal to the number right before it plus 2. A5 is equal to the number right before it plus 2. So A sub n, right? I need some way to use my notation to write the number right before A sub n. Yes, right? 1 smaller than n is n minus 1. So in this notation, I'm going to put A sub n minus 1. That means the number right before the nth number, plus 2. So that sub n minus 1 is an important notation that we're going to use a lot in the rest of the semester. We're going to be using this subscript notation. So this just says, if I replace n with anything, like if I replace n with a 10, right, A sub n minus 1, that would be A sub 9. Kind of make sense? Okay. So this last thing that I wrote here, we call that a recursive rule for a sequence. Okay. We call a rule recursive if it uses previous terms of the sequence to calculate the current term. So to calculate A sub n, I need to know A sub n minus 1, the term before it. So this is called a recursive rule because to get A sub n, the current term, I need to know a previous term. All right, same sequence. I'm going to identify the pattern in a different way now. A sub 1 is 2, right? So if I wanted to write 2 as 2 times something, what would my something be? 1. And A sub 2 is what? 4. And if I want to rewrite 4 as 2 times something, what would my something be? 2. And A sub 3, which is 6, is 2 times something. What's my something? 3. So I put a 3 here. So A sub 4, without writing out the stuff on top, what do you think is going to go in the blank here? 4, yeah. The number that's going in this blank is the subscript, right? A1 is 2 times 1. A2 is 2 times 2. A3 is 2 times 3. A4 is 2 times 4. So what would AN be? 2 times n. The subscript, you always double the subscript, and that gets you the value, right? So this just says that the fourth number in the list is 2 times 4. And the second number in the list is 2 times 2. The third number in the list is 2 times 3. So this is another way to describe the pattern of the even numbers. The nth number in the list is just 2 times n. So if I wanted to know the 16th number in the list, I would just do 2 times 16. And I would say, oh, the 16th number in the list is 32. Without having to write out the whole list. And in this case, if I want to know the nth term, I don't need to know any terms before it, right? I could calculate the 100th term in the list by just doing 2 times 100. I would get 200. And I did not need to know the 99th term in the list. If I used this formula and I wanted to know A100, the 100th term in the list, I would have to know the 99th term and add 2 to it. So these are 2 different ways of describing the same pattern. This one is called recursive, and this one is called explicit. Recursive, explicit. So we call a rule explicit if all you need to know to calculate the nth term is the value of n, as opposed to other values in the sequence. All right, so we're going to play a little game called Guess My Rule. I'm going to have you think about this in your groups. Work on these first two problems. And then we'll go over them after. All right, so let's go over these a little bit. So anybody come up with what S sub 5 should be? 7.5, and S sub 0, a little bit trickier? 0, yeah. So S sub 5 is 7.5, and S sub 0, 0. Now, if you came up with those two things, you have all of the knowledge to answer the next two problems. All you have to know how to do is translate what you saw as a pattern, because you had to see the pattern to get these, right? So all you have to do is be able to translate from English, from the pattern that you saw in English, to this new notation that we're using with the little subscripts and the ends. All right, so can somebody explain to me how they figured out 7.5 has to be S sub 5? Okay, so these values, S sub n's, are increasing by 1.5 at each transition, right? Good. So I'm going, each one's increasing by 1.5. Okay, so let's write that rule in English. So each term is the term before it plus 1.5, right? That's the pattern that you saw. Oh, every term is the term before it plus 1.5. Everyone agree so far? Okay. So now all I have to do is translate this to the mathematical notation we're learning that uses the subscripts and the n's and the s's, right? So if I want a recursive rule for S sub n, that stands for sort of a generic term in the sequence. How would I figure out what S sub 12 is, what S sub 16 is, right? So n could represent anything. So I want a formula for how to calculate the nth term in the sequence. So S sub n is. So each term translates to S sub n. S sub n is just representing a generic term. Okay, is equals the term before it. How can I use my new notation to indicate the term right before S sub n? S sub n minus 1, right? So instead of the nth, the n minus first term, the term right before the nth. So if n were a 12, right, this would say S sub 12, the 12th term in the list, is equal to S sub 12 minus 1, which is 11, right? But then I have to add 1.5 to it. Okay. So if n were 18, if I wanted to find S sub 18, I would take S sub 17, right? 18 minus 1 is 17, and add 1.5 to it. No, because S sub 17 isn't necessarily 17. 17 is just the address in the list, right? So this is my recursive rule. So all we have to do is learn how to translate from recognizing the pattern in English to using my subscript to do it. And the term before it is the trickiest part, right? Going to use an S sub n minus 1. All right, now an explicit rule. So often the explicit rule is a little bit harder to find. So in an explicit rule, I have to write S sub n equals, right? But I can't use any other terms in the list. So I can't use S sub n minus 1 in my formula. All I can use is n. So if I want to find out S sub 25, the only number I'm allowed to use in my calculations on this side of the equal sign is a 25. Okay, so now I have to look at the relationship between n and S sub n, right, instead of the relationship between the values of S sub n. So how is 1 related to 1.5? How is 2 related to 3? 3 related to 4.5? 4 related to 6? Close. That's it. Times 1.5, which is 150%. Is that what you said? Yeah. So you want to multiply the n value by 1.5. 1 times 1.5 is 1.5. 2 times 1.5 is 3. 3 times 1.5 is 4.5. 4 times 1.5 is 6. 5 times 1.5 is 7.5. So you can think of that as multiplying by 1.5, taking 150% of the value, increasing the value by 50%. But the way I'm going to write the formula is I'm going to say take your n value and multiply by 1.5. And that will tell you the S sub n value. Backwards, what do you mean? Oh, that's not backwards. You can do multiplication in any order you want. So you can write this as 1.5 times n, no problem. So recursive rules look at the relationship between values in the row S sub n. And the explicit rule looks at the relationship between n and S sub n in the columns. Right? Is this kind of okay? Okay. Why don't you take another try at looking at, oh, sorry, I should say, S is a special kind of sequence, this one that we just talked about. A sequence where the rule to get from one term to the next is to add or subtract a constant amount, in this case 1.5. To get from one term to the next, we just add 1.5. Where you add any constant, that's called an arithmetic sequence. So it's just a little special name for that kind of sequence. So here's another sequence, G. Take a stab at coming up with G5, G0, and a recursive rule. Do this part and this part. Think about this part if you have time, but this part is tricky, so we'll definitely go over that part together. All right, so let's look at the, first just try to figure out what G5 and G0 are. And I saw two different ways that people were coming up with this. So one is that people looked at addition, right? They said, oh, okay, to get from 5 to 10, we do plus 5. To get from 10 to 20, we do plus 10. To get from 20 to 40, we do plus 20. And they said, oh, look, you do 5 plus 5. So you do 5 plus itself, and you get 10. We do 10 plus itself, and you get 20. 20 plus itself, and you get 40. So this would be 40 plus itself, and you get 80. So G sub 5 would be 80. All right, so another way to come up with G sub 5 is 80 is to say, instead of thinking about adding, think about multiplying. What do you multiply 5 by to get 10? 2. What do you multiply 10 by to get 20? 20 to 40 times 2. And then times 2 would get you 40 to 80. So you can think about it as adding itself, which is the same thing as multiplying by 2, right? That's the definition of multiplication, is repeated addition. 5 plus 5 is the same as 5 times 2. 10 plus 10 is the same thing as 10 times 2. That's what multiplication means. So if I want to go backwards in the list, right? If to go forwards you multiply by 2, what would have to come before the 5? 2.5, so that when you double it, you get the 5. Yeah. Yeah, so we take the 5 and you divide by 2 to go one step backwards in the list. So depending on how you thought about this pattern, we could have two different answers for this recursive rule. And I saw two different answers as I walked around that are actually equivalent. Okay, so one, we would say, well, G sub n is, using this times 2 times 2 times 2, you would say it is the previous term in the sequence, which is what? G sub n minus 1 times 2, right? You just take the previous term and double it. Or if you looked at it the first way that we looked at this with the addition, plus 5, plus 10, plus 20, plus 40, you said, okay, we're taking g sub n minus 1 and adding the same thing, right? So g sub n minus 1 plus g sub n minus 1. And these are equivalent, right? Because adding a number to itself is the same thing as multiplying that number by 2. So those two formulas are exactly the same, just a different way of expressing it. So depending on how you saw the pattern, you might have written one of these two down. Okay, the explicit rule is trickier. But before we move on, anybody still have questions on the recursive rule? All right, so let's look at the explicit rule. And I'm going to make a little table to make this a little easier for myself. N, G sub n. And we'll start with 1, 5, 2, 10. Okay, so 1, 5. So in this third column, I'm going to write the value of G sub n again. I'm just going to write it in a different format. So this is going to be 5. We'll leave it as a 5. And 10 we got by taking 5 times 2, right? That's how we calculated the 10. We doubled the previous G value. All right, and then to get to the 20, we did that by taking this 10 and doubling it, right? This is 10 times 2 to get 20. But instead of writing it as 10 times 2, I'm going to write the 10 as a 5 times 2 and double that. And then to get to the 40, I double the 20, right? I take 20 and multiply it by 2. But instead of writing 20 times 2, I'm going to write 20 as 5 times 2 times 2 and double that. So actually, let me make this a little bit clearer. This is 10 times 2. That's how we got the 20, which is 5 times 2 times 2. And then the 40, that's 20 times 2. But rewrite 20 as 5 times 2 times 2. So this is 5 times 2 times 2 times 2. And then the next number in the list is 80. And the way you get 80 is you take the previous number in the list, 40, and double it. But 40, we know we can rewrite as 5 times 2 times 2 times 2. So this is 5 times 2 times 2 times 2, and then double that times 2. So repeated multiplication, how do we denote that in mathematics? What's the special thing we use? An exponent. So this one is 5 times 2 to the first. This one is 5 times 2 squared. This one is 5 times 2 cubed. This one is 5 times 2 to the fourth. This one is 5 times 2 to the, what? It's just 5. So how do I write it as 5 times 2 to the what? 0, right? Because you guys remember that? Anything to the 0 is really 1. So that says 5 times 1, which is 5. Okay, so let's look at the relationship. So G sub n, I can always write G sub n as 5 times 2 to something. So let's go back to my place where I'm trying to write a formula. And I'm going to say, okay, I can always write G sub n as 5 times 2 to something, right? And the question is, what is that something? I can only use n's here, the subscript. So I have to figure out how this exponent is related to the subscript. So let's go back to the table. And I want to look at my subscript and my exponent. Subscript, exponent. Subscript, exponent. It's 1 smaller, right? When the subscript is 1, my exponent was 0. Subscript of 2, exponent is 1. Subscript of 3, exponent is 2. When n is 4, my exponent is 3. So my exponent is always going to be 1 smaller than the subscript n. So I go back here, and what goes in here, how would I write something 1 smaller than n? N minus 1. So there's my explicit formula. G is a special kind of sequence also. A sequence where the rule to get from one term to the next is to multiply, right? Like times 2. Or divide by a constant is called a geometric sequence. Okay, so that finishes up the lecture.